Typhoon Fong Wong terrifies scientists again by what they found. This storm is not just coming back, it is returning stronger, more dangerous, and behaving in ways that defy everything meteorologists thought they knew about how typhoons work. Picture a massive storm that already devastated the Philippines with 185 kilometers per hour winds and record-breaking rainfall, now reforming in the Pacific with even more destructive power. This is a meteorological nightmare that is rewriting the rules of tropical cyclone behavior in real time. But here is what has weather experts in complete panic. Fong Wong is not just regenerating, it is showing signs of rapid intensification that could turn it into a super typhoon within hours. Satellite data reveals the storm is drawing energy from sources that should not exist, creating a feedback loop that makes it stronger with each passing hour instead of weakening like normal storms do. The most terrifying discovery came from analyzing the storm's internal structure. Fong Wong is maintaining its eye wall integrity in ways that suggest it has become a self-sustaining weather system that could potentially last for weeks, repeatedly striking the same devastated areas that are still recovering from its first assault. Is Fong Wong's return just a freak weather event? Or are we witnessing the birth of a new type of superstorm that could make traditional typhoons look like gentle rain showers compared to this meteorological monster? Seismic monitoring networks detect the pattern first, but it is the meteorologists at Pagasa headquarters who grasp its impossible implications. At 2:17 a.m. Philippine Standard Time on November 18th, automated weather buoy WB-47, positioned 240 kilometers east of Aurora Province, registers an 8 millibar drop in barometric pressure over the previous 6 hours. For any other monitoring station, such a reading might indicate normal atmospheric variability, but WB-47 sits directly along the dissipation track of Typhoon Fong Wong, a storm that made catastrophic landfall just 72 hours earlier. The pressure signature suggests not decay, but reorganization. Senior meteorologist Dr. Elena Reyes examines overnight data streams from multiple sensor networks, each one confirming a trend that defies textbook typhoon behavior. Fong Wong's remnant low-pressure system, which should be dispersing across the South China Sea, instead shows signs of renewed convective activity. Satellite imagery from the Himawari 9 platform reveals cloud-top temperatures dropping to -70 degrees Celsius, the thermal signature of intense thunderstorm development typically associated with strengthening tropical systems, not dying ones. Sea surface temperature measurements record water temperatures of 30.2 degrees Celsius, a full 1.4 degrees above the long-term seasonal average. At these temperatures, the ocean becomes a massive heat engine capable of feeding tropical cyclones with enormous quantities of energy. Upper-level atmospheric analysis reveals wind shear measurements of less than 10 knots, removing the natural break that typically decapitates developing storms. Dr. Reyes pulls up historical typhoon dissipation data spanning 40 years of satellite observations. Standard meteorological understanding holds that typhoons weaken rapidly over land, requiring 5 to 7 days minimum before any possibility of regeneration over open water. Fong Wong is re-intensifying within 72 hours. Computer analysis finds no comparable cases of reorganization of the same storm occurring this rapidly after a major landfall. The reformation window violates every historical precedent in the database. The Baylor Doppler radar installation, positioned on a ridge 340 meters above sea level with unobstructed views across Aurora Province and the Philippine Sea, went dark at 11:23 p.m. during Fong Wong's initial assault. The facility's primary radar dish, designed to withstand wind speeds up to 200 kilometers per hour, suffered catastrophic structural failure when a sustained gust exceeding 240 kilometers per hour tore through its mounting assembly. Engineers arriving at first light found the entire monitoring complex inoperable, leaving a surveillance gap of 200 kilometers along the coast, precisely where Fong Wong's reformation was now occurring. 4 coastal tide gauge stations that provide real-time sea level measurements, essential for storm surge warnings, failed within hours of each other as the typhoon made landfall. The Baylor station, equipped with acoustic sensors capable of measuring water height changes to centimeter precision, lost telemetry at 9:47 p.m. when storm surge overwhelmed its protective housing. Casiguran's tide gauge, located 40 kilometers north, transmitted its final reading at 10:15 p.m., showing water levels 3.8 meters above normal before the data stream ceased. Apari and Infanta stations followed in sequence, their communication links severed by wind damage to transmission towers. 3 automated weather stations in eastern Luzon experienced complete data feed interruptions lasting over 18 hours. Station AW23 near Dingalan lost power when transmission lines snapped. Station AW31 in Bongabon continued transmitting corrupted data packets, suggesting water intrusion in its sensor array. Station AW45 at Palayan went completely silent at 2:34 a.m. Dr. Jennifer Santos, lead forecaster at the Pagasa Operations Center, reviews the overnight damage assessment with growing concern. The monitoring network now operates at 30 to 40% capacity across the critical northeastern quadrant of Luzon. Forecasters attempting to analyze Fong Wong's reformation work with data gaps spanning hours and covering hundreds of square kilometers. The degraded monitoring capability creates dangerous blind spots, precisely when detailed observations are most critical for tracking a storm that defies every historical precedent. At 6:15 in the morning on November 19th, Mayor Joel Batong receives the call that transforms preparation into crisis. Pagasa's regional coordinator delivers the assessment with clinical precision. Typhoon Fong Wong has re-intensified to signal number 4 strength, and Dinalongan sits directly in the projected impact zone. The mayor stands in his municipal office, surrounded by damage reports from the first landfall still scattered across his desk. 3 evacuation centers remain at capacity, housing 4,800 residents whose homes suffered roof damage or flooding. The community's emergency supplies, carefully stockpiled over months, depleted to 40% of original levels during the initial disaster response. Batong convenes his disaster council at 7 in the morning, the faces around the conference table reflecting exhaustion and disbelief. The municipality's evacuation capacity calculations reveal an impossible mathematics. The 3 functioning shelters can accommodate 6,200 people under emergency conditions. Current occupancy sits at 4,800 from the first storm. Pagasa's latest advisory places an additional 8,000 residents in the mandatory evacuation zone for the approaching second landfall. The numbers simply do not reconcile. Transportation infrastructure assessments compound the challenge. The coastal road linking Dinalongan to inland evacuation routes sustained damage at 7 locations, where storm surge undermined pavement and weakened bridge approaches. Engineers estimate 60% of normal traffic capacity remains on the primary evacuation corridor. The backup route through the mountains requires an additional 90 minutes of travel time, and recent landslides triggered by Fong Wong's initial rainfall have left sections vulnerable to complete closure. The mayor issues evacuation orders at 8:30 in the morning, knowing the timeline provides perhaps 48 hours before the reformed typhoon makes its second strike. Police and barangay officials deploy across coastal zones, moving door to door through neighborhoods where families have just begun salvaging belongings and repairing damage. Some residents refuse to leave, traumatized by the first evacuation and unable to face abandoning their homes again. Batong authorizes forced removal if necessary, repeating the grim directive that saved lives during the initial landfall. In the analysis laboratory of Pagasa's Science Garden facility, Dr. Michael Chen processes satellite data that reveals mechanisms no textbook predicted. Himawari 9 infrared scans, collected in 10-minute intervals throughout Fong Wong's landfall and aftermath, create a time-lapse sequence of the storm's internal structure. What emerges from the enhanced imagery defies conventional understanding of tropical cyclone dissipation. The typhoon's core circulation, which should have collapsed upon encountering Luzon's Sierra Madre mountain range, instead maintained a coherent low-level vortex, even as the eye wall disintegrated against terrain, rising to 1,800 meters elevation. Sea surface temperature analysis provides the first piece of the reformation puzzle. NOAA buoy arrays positioned across the Western Pacific record sustained temperatures of 30.2 degrees Celsius, representing a positive anomaly of 1.4 degrees above climatological averages for mid-November. Ocean heat content measurements, which quantify thermal energy stored in the upper 200 meters of the water column, show values exceeding 110 kilojoules per square centimeter. These readings indicate an oceanic heat reservoir capable of supplying energy to tropical systems at rates that can sustain rapid intensification even in marginal atmospheric conditions. The Madden-Julian Oscillation, a globe-circling pulse of enhanced tropical convection with a 30 to 60-day cycle, entered an active phase over the Western Pacific precisely as Fong Wong's remnants drifted offshore. Atmospheric analysis reveals this oscillation brought a surge of equatorial moisture and reduced wind shear across a region spanning 3,000 kilometers. The timing alignment, calculated by meteorologists as having less than 8% probability in any given month, created atmospheric conditions favoring rapid storm development exactly when Fong Wong's circulation re-encountered the superheated ocean surface. Vertical wind shear measurements from upper air balloon soundings show values dropping to 6 knots between the surface and 12 kilometers altitude. Computer models calculate that shear below 10 knots removes the primary atmospheric constraint preventing tropical cyclone organization. Without this disruptive force, convective towers can maintain vertical alignment, allowing the thermodynamic engine of a developing typhoon to operate with maximum efficiency. Satellite-based microwave sounders detect atmospheric moisture content approaching 75 millimeters of precipitable water, fuel sufficient to generate and sustain the intense thunderstorm complexes that power typhoon intensification. Computer modeling laboratories at the Philippine Institute of Volcanology and Seismology run storm surge simulations around the clock, processing thousands of variables that distinguish this approaching disaster from conventional typhoon scenarios. The models incorporate a critical factor absent from standard forecasts: infrastructure already compromised by catastrophic damage. In Baylor Bay, seawalls designed to withstand 3-meter surges now contain structural cracks and undermined foundations from Fong Wong's initial assault. Engineers estimate the damaged barriers can sustain perhaps 60% of their original design load before catastrophic failure. Storm surge calculations for the reformed typhoon predict water levels reaching 5 to 6 meters above mean sea level at high tide. The projections account for Baylor Bay's funnel-shaped coastline that amplifies surge through geometric concentration, forcing ocean water into progressively narrower channels. Computer simulations show the surge propagating inland across low-lying areas already saturated from the first storm's 400 millimeters of accumulated rainfall. The compound flooding scenario, where storm surge meets swollen rivers draining from mountainous terrain, creates inundation patterns extending 800 meters beyond the original flood boundaries. Landslide risk modeling reveals exponentially increased danger across slopes destabilized by initial rainfall. Soil moisture sensors installed throughout the Sierra Madre foothills record saturation levels at 85 to 95% of maximum capacity. Additional rainfall projected at 300 to 500 millimeters will push these slopes beyond their critical threshold, triggering debris flows that computer models predict could reach volumes 3 times larger than those generated during the first landfall. The simulations identify 27 communities situated directly in potential mudflow paths, representing approximately 34,000 residents in zones where evacuation time could measure in minutes rather than hours. Building structural assessments conducted by engineering teams reveal compromised integrity across thousands of structures. Residential buildings that sustained roof damage and wall cracking during the initial typhoon now face wind loads they were never designed to withstand in their weakened condition. Computer analysis estimates collapse probability, increasing by 200 to 300% for structures previously damaged. Evacuation centers themselves, stressed beyond capacity, and showing minor structural damage from the first storm, must now shelter populations while facing a second catastrophic impact that could exceed the forces that initially damaged them. Dr. Ronald Villarine, an atmospheric scientist with the Manila Observatory, examines atmospheric chemistry data that points to systematic shifts in Western Pacific storm behavior. 5 distinct environmental factors have converged to create conditions that challenge fundamental assumptions about tropical cyclone energy limits. The Western Pacific sea surface temperature anomaly reached 1.4 degrees Celsius above normal during Fong Wong's reformation period, with measurements sustained across a region exceeding 800,000 square kilometers. Historical analysis of typhoon intensification rates shows a direct correlation between sea surface temperature anomalies above 1 degree and rapid strengthening episodes. But the current thermal surplus exceeds any recorded during the satellite era, beginning in 1979. Ocean heat content measurements reveal the subsurface thermal structure supporting unprecedented storm energy transfer. Autonomous profiling floats deployed across the Philippine Sea record temperatures exceeding 29 degrees Celsius to depths of 150 meters, creating a thermal reservoir that resists cooling even under sustained typhoon wind forcing. Computer calculations show this deep, warm layer can supply heat energy to tropical cyclones at rates 40% higher than conditions present during the formation of previous super typhoons, effectively removing the oceanic feedback mechanism that normally limits storm intensification. The Madden-Julian oscillation phase alignment provided atmospheric conditions that occur with statistical frequency of once every 3 to 4 years. Atmospheric soundings detect enhanced convective activity and reduce subsidence across the Western Pacific, creating an environment where rising air parcels encounter minimal resistance. This oscillation phase typically persists for 10 to 15 days, but current forecasts show the favorable pattern extending beyond 20 days, an unusually prolonged window for storm development. Atmospheric moisture analysis reveals persistent water vapor concentrations exceeding 70 millimeters across the storm formation region. Satellite-based microwave radiometers trace this moisture to a quasi-stationary trough positioned northeast of the Philippines, channeling equatorial humidity directly into Fong Wong's circulation. The moisture influx sustains rainfall rates and latent heat release that power the storm's convective engine. Vertical wind shear measurements show sustained values below 8 knots, removing the atmospheric constraint that typically disrupts tropical cyclone structure. Dr. Villarine states the combined occurrence of these 5 factors represents conditions with less than 2% annual probability under historical climate patterns. At 9:15 a.m. on November 20th, Pagasa issues its most sobering forecast update. Typhoon Fong Wong, now centered 420 kilometers east-northeast of Aurora Province, has re-intensified to super typhoon status, with maximum sustained winds of 195 kilometers per hour and gusts reaching 240 kilometers per hour. Barometric pressure at the storm's center has dropped to 935 millibars and continues falling at rates that suggest further intensification remains possible. The forecast track places landfall in northeastern Luzon within 72 hours, targeting communities still recovering from devastation inflicted during the storm's first strike. Pagasa raises the alert level to signal number 5 for Aurora, Isabela, and portions of Cagayan provinces. This marks the first documented case in Philippine meteorological history where the same tropical cyclone generates 2 separate signal number 5 warnings for overlapping geographic areas. The advisory expands mandatory evacuation zones to cover an additional 800,000 residents beyond the 1 million already displaced by the initial landfall, creating humanitarian logistics challenges that exceed the combined capacity of regional and national emergency response systems. Evacuation centers designed for temporary occupancy now house populations approaching 150% of rated capacity. Medical teams treating injuries and illnesses from the first storm face the prospect of providing care during a second catastrophic impact, while their facilities remain structurally compromised. The Philippine Coast Guard positions vessels for search and rescue operations, despite equipment damage sustained during initial response efforts. Crew fatigue and mechanical failures limit operational readiness to approximately 70% of normal capability. International assistance begins mobilizing as the scale of the unfolding disaster becomes clear. United States military humanitarian response teams prepare airlift assets. Regional meteorological centers contribute computational resources to forecast modeling efforts that are struggling to predict behavior, which appears to violate established atmospheric physics. Emergency supply stockpiles prepositioned across Luzon face distribution challenges as damaged roads and bridges limit access to communities most at risk. Dr. Elena Reyes addresses media during the afternoon briefing, her assessment direct and sobering. The meteorological community is witnessing storm behavior that exceeds the boundaries of current scientific understanding. Forecast confidence intervals remain wider than normal, reflecting genuine uncertainty about a system that has already rewritten the rules. She says the reformation timeline and intensification rate have no historical precedent. Typhoon Fong Wong continues its approach toward northeastern Luzon as monitoring networks track its every movement with a mixture of scientific precision and acknowledged uncertainty. The storm that meteorologists once declared impossible now dominates satellite imagery, its perfectly organized structure challenging textbook assumptions about tropical cyclone behavior. Across Aurora Province and surrounding regions, 1.8 million people wait in evacuation centers, damaged homes, and reinforced structures, bracing for an impact that computer models struggle to quantify with confidence. What makes this storm unprecedented extends beyond its reformation speed or intensification rate. Fong Wong represents the convergence of multiple factors that individually would concern meteorologists, but together create conditions outside the envelope of historical experience. The 72-hour reformation window violates 4 decades of satellite-era observations. The double strike on identical geographic areas compounds disaster in ways emergency planning never anticipated. The atmospheric and oceanic conditions enabling this behavior suggest patterns that climate science predicted, but hoped would emerge more gradually, allowing time for adaptation. The scientific measurements tell a story that extends beyond one exceptional typhoon. Western Pacific sea surface temperatures are elevated 1.4 degrees above normal. Ocean heat content is at record levels down to 150 meters depth. Atmospheric moisture concentrations are exceeding historical ranges. Vertical wind shear collapsed during critical formation periods. The Madden-Julian oscillation alignment provided extended favorable conditions. Each factor represents a piece of evidence pointing toward a climate system operating under new constraints, generating storm behavior that challenges fundamental assumptions about what tropical cyclones can do. Unprecedented forces are showing themselves. Infrastructure designed for historical storm parameters faces forces it was never built to withstand. Forecasting models trained on past patterns struggle to predict futures that have no analog. Communities develop resilience based on experience, but that experience becomes inadequate when the rules change faster than adaptation can follow. The monitoring stations continue their vigil. Seismometers, satellites, and tide gauges are recording data that will eventually inform better understanding. For now, the measurements accumulate as Fong Wong approaches, writing a new chapter in the meteorological record. The playbook is being rewritten in real time, and millions are living through the first draft.